Ready to jiggy wiggy, whatever that means. We're ready to get going with the live, with the information, with the giant moons topic. Look at this. Look at these people. Look at these kitty cats. Look at the kitty cats. Look at it. Look at the kitty cats. We're talking about the giant moons today. We're talking about the gigantic moons of the solar system. So, all right. We already talked about some of these moons, but we will recap. We will recap for you. So, first things first. First things first, we already talked a little bit about the Earth and our own moon, which actually happens to be one of the giant moons. So indeed, it's going to be interesting because it's going to be the giant moons, that is, will include our moon, Jupiter's Galilean moons, Saturn's moon, Titan, and Neptune's moon, Triton. So we kind of talked about the Galilean moons of Jupiter yesterday, but we will sort of recap them today. We will sort of recap them today. I had to turn off the gigantic light on my face. But yes. Thank you for liking. Thank you for liking the live. Thank you for liking the live. And thank you for being here. Sorry we're late. We should have gone live in the afternoon. But we're here now. So our Earth has a moon, and it also happens to be one of the giant moons of this solar system. It is, in mass, it is 0.0123 times the mass of Earth, and in radius, it is 0.27 times the radius of Earth. We will consider all of these giant moons and give you the information in terms of the mass and radius of the Earth. The next thing is Jupiter has 4 of the giant moons of the solar system. These are Io, Europa, Ganymede, and Callisto. We talked about these yesterday, but we will kind of see them again today. And these basically have masses from 0.0150 to something like 0.008, 0.24, 0.1 in the case of Callisto. Ganymede is the biggest one, and it has a mass of 0.0248, the mass of the Earth, and a radius of 0.41, the radius of the Earth. So it's really huge. It's the biggest one. Largest satellite in our solar system is Ganymede, which is, of course, one of the moons of Jupiter, and that too one of the Galilean moons. So Galileo was the one who discovered these 4 moons of Jupiter, and it was historically very significant because it told us that other planets too had satellites. It wasn't just us, Earth, who had a moon, which was making us feel very special. Indeed, we are very special. This moon is very special, but we just have the one. Whereas now there were other planets too that had satellites, and it was further sort of evidence towards the Copernican system versus the Ptolemaic system. So heliocentric versus Earth-centric solar system. So these 4 moons we kind of covered yesterday, but again, they are Io, Europa, Ganymede, and Callisto. Then we will also have Titan, which is a moon of Saturn, and this is also a giant moon, and we will talk about that today. And then we have Triton, Triton. This is a moon of Neptune. We will also talk about that today. Manoj, you know, I was encouraging you to utilize your intellect, but it seems I have to put you in timeout instead, all by myself, because my mods are busy right now. You can stay on the live, but let's hold off on your comments for 30 minutes. I'm very lenient. My mods would probably ban you forever. So just be careful. if they join they do troll a lot of the trolls. So it becomes a bloodbath before we know it. Okay. Aw. I think he left. Aw. So sad. So Ganymede is the third Galilean satellite. It's the largest one. Let me real quick cover, you know what? Let me do this. Let me make sure that we can cover Titan, which is the moon of Saturn, because we did finish up the Galilean moons yesterday. So I just want to make sure that I cover the ones that we haven't covered. And then I can always, if there's time, come back to the Galilean moons of Jupiter. In short, I will just say that yesterday we covered the Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, and they're all kind of different from each other, all very interesting in different ways and kind of different from each other. So if you want to, see that material more in depth, including some of the pictures and everything that we showed on about the moons, about their surfaces, which are all kind of different, then yesterday's live has that. But today, let me start with Titan because we covered up to Jupiter already. Okay, so Titan is the giant satellite of Saturn, and it's observed to have a thick atmosphere with a surface pressure of 1.6 atmospheres. Now, remember, we've been talking about some very extreme environments when it comes to Jupiter and Saturn, of course. We haven't gotten too much into Uranus and Neptune because remember, for the Jovian planets, which is of course Jupiter, Saturn, Uranus, and Neptune, Jupiter and Saturn are kind of in a group and Uranus and Neptune are kind of in a different group. Okay, so Jupiter is almost like its own, it really belongs to its own league. Most other planets, actually pretty much all other planets, are not really like Jupiter. Jupiter has a tremendously extreme size and mass. Its mass is 318 times the mass of Earth. So all of this taken together gives it a very extreme environment. So before I get into the details of the planet of the satellites, I just wanted to say that remember from I think a couple of lives ago when we were covering more about Jupiter and Saturn, we saw that they have tremendous central pressures, like in the millions of atmospheres. So inside of Jupiter and Saturn, the pressure is very, very high. And let's compare it to the pressure on Earth here at sea level. At sea level on Earth, we have a pressure which we call 1 atmospheres in the atmosphere unit. There is also another unit of pressure called newtons per meter squared, which of course is a force divided by an area. In the standard way, we just say newtons per meter squared, but there's another unit which is in atmospheres, and for reference, at sea level, we have an atmospheric pressure of 1 atmospheres. Okay? So this 1.6 atmosphere number gives you some idea that's kind of like, it's similar-ish to Earth. It's not a whole lot more than the pressure on Earth at sea level, but it is very much less than some of the pressures that we've been talking about with regard to Jupiter and Saturn. But this is, of course, a satellite of the planet, not the planet. So this is the satellite of Saturn. So let's see. Let's see what this thick atmosphere is made of. Also, another thing I will note is that remember how depending on your distance from Jupiter, for example, we're talking about Saturn, but remember how each of the moons of Jupiter were very much affected by their distance from the planet. Because Jupiter outputs a lot of heat and energy, if you're very close to Jupiter, you're going to experience a very much more extreme environment. And basically Io, the moon that was closest to Jupiter, had a very sort of a thin atmosphere because its atmosphere is basically kind of getting trapped in, yes, peanut butter, would get trapped in the magnetic field of Jupiter. And then, but also Io has a very geologically active site, as it is the most geologically active site, turns out, in the solar system. It has a lot of volcanoes, so it constantly spews out more things into the atmosphere, mainly sulfur and sodium, and then it has sort of a thin atmosphere again, but then again that's taken away sort of by the magnetic field of Jupiter. Okay, so if one of the giant satellites has an atmosphere, that's pretty interesting. Not all of them do. Not all of them experience the same sort of very extreme environment as you would. For example, if you were close to Jupiter, and the story is kind of different based on which one you're on. Okay. So Titan, very famous moon of Saturn, and of course the giant, one of the giant moons, just period, in this solar system. Let's see, what is its size? Titan is 0.40 the radius of Earth. So Titan is only a little bit smaller than Ganymede in terms of its radius. And it's quite massive too. It is 0.0225 times the mass of the Earth, which is also pretty big. I'll compare that to our moon, which is 0.0123. So 0.01 versus 0.02, quite a bit different in mass. And then also, yeah, the radius is pretty big. It's only slightly smaller than the radius of Ganymede. So if I'm looking at this correctly, I believe Titan is the second largest satellite in the solar system. Okay, pretty interesting. So Titan, the giant satellite of Saturn, is observed to have a thick atmosphere with surface pressure of 1.6 atmospheres. It consists primarily of nitrogen. Oh, how nice! With smaller amounts of argon and hydrocarbons such as methane and ethane. So methane is CH4, ethane is C2H6. Random guy says peanut butter. Hello. So that's what's in the atmosphere of Titan. So we have argon, nitrogen, methane, and ethane. The atmosphere of Titan is readily apparent in a view of Titan backlit by the sun. Wow. In a view of Titan backlit. Oh my gosh, there's a very nice picture here. I will show it to you in just a second. So atmosphere of Titan is readily apparent in a view of Titan backlit by the sun, since the refraction of sunlight by the atmosphere makes it look like a ring of light. So the nice thing about having an atmosphere is that light will, refract off of that, will get affected by it, and it shows up in a different way. And let's just look at it. So sunlight striking the atmosphere triggers the polymerization of hydrocarbons. The resulting long hydrocarbon chains constitute a smog layer in the upper atmosphere. The temperature and pressure in Titan's atmosphere is close to the triple point of methane. Interesting. As a consequence, methane can exist on Titan in its gaseous, liquid, and solid forms. So triple point of methane, it can be both, it can be all three: gaseous, liquid, solid, everything. Infrared images of the surface of Titan taken by the Cassini spacecraft indicate that Titan may have lakes of liquid methane and ethane on its surface. Lakes of methane and ethane. Wow. That's something, huh? So that is Titan. Sorry. I'm going to dinner soon. But this is my appetizer. So, welcome, welcome. Thank you for being here. Let me show you the picture. That's the picture. Wow. Look at that. A view of Saturn's rings in front of... Oh, that's right. In front of that thing that I just showed you is Saturn's rings. So I will show this picture to you in more detail, but this is going to have a view of Saturn's rings in front of Saturn's giant satellite Titan. Yeah, no lake, no swimming in the lakes. The image was taken in visible light by the Cassini spacecraft. The Sun-Titan spacecraft angle was 158 degrees. Wow. So yeah, unless you want to swim in methane and ethane, these wonderful lakes of liquid methane and ethane on Titan might be a little uncomfy, but that's so beautiful though. I feel like liquid lakes are such a beautiful thing to have. Okay, let me put this away. So very interesting indeed. So very, very interesting. Oh, there's Baji behind me. Oh, Baji. Oh, Baji. Oh my goodness. Oh my goodness. Okay, so I think here, Fuji, you want this box? I think what we might do now is it is flammable, yes. I guess don't don't make a fire on Titan. Fuji's on the book. I can't read from it because Fuji is sitting on it. Hi, Fuji Babu. Fuji, do you want to sit on this box, maybe? Uranus and Neptune are twin planets similar in their properties. I can still read a little bit. Uranus is 3% larger in radius than Neptune, but 15% smaller in mass. So now we're talking about Uranus and Neptune. Their internal structure is quite similar, with a layer of ordinary molecular hydrogen lying atop a layer of liquid water and ammonia. Isis, in the jargon of planetary scientists, in turn lying atop a solid rocky core. So we talked about how Jupiter and Saturn have this layer of metallic hydrogen, and Uranus and Neptune don't. Wow, I got the book back. Jupiter, in fact, has a very gigantic metallic hydrogen layer that we read about. And now we're on Uranus and Neptune. Before we can talk about the last giant moon, Triton, which is the moon of Neptune, I figure we should probably cover Uranus and Neptune as well. So I will show you. Oh, first let me show you, now that I have the book back, this is that Titan with its atmosphere, and this in front is the Saturn ring. So this is a picture by Cassini showing us a view of Saturn's rings in front of Saturn's giant satellite Titan, okay? Right here, behind this ring is Titan. So that's the picture that I was going to show you. And then let me also show you, while I have the book. Hello, random guy. Hello, everybody. Thank you for being here and thank you for commenting. Let me show you these ice cream cones. This is Jupiter, this is Saturn, this is Uranus, and this is Neptune. So, yes, indeed, I said that right. So see how Jupiter and Saturn have a so especially Jupiter, this is the metallic hydrogen layer of Jupiter. Okay, so see how the last two ice cream cones have just 3 layers? Those are Uranus and Neptune. See how the first 2 ice cream cones have 4 layers, and that's because Jupiter and Saturn have an extra layer made of metallic hydrogen that we talked about, I think a few lives ago. So let me just say the layers again for each of the planets so that it refreshes, it's like a recap, okay? So Jupiter has a bit of rock, and this is all relative, right? Bit is really a lot. Basically Jupiter, it's like having a rocky planet at its core is basically its core, right? Like one of the rocky planets, or one of the terrestrial planets, which of course include us, Earth, Venus, Mercury, and Mars. But anyway, compared to the other layers, Jupiter has a bit of rock, then ice, then a lot of metallic hydrogen, and then molecular hydrogen as the 4 types of layers. Saturn has, again, a bit of rock, ice, metallic hydrogen, not as big metallic hydrogen layer as Jupiter, but still a metallic hydrogen layer, and then molecular hydrogen. And then Uranus and Neptune basically just have the rock, the ice, and molecular hydrogen. They don't have the metallic hydrogen because basically the metallic hydrogen is because of the very extreme central pressure in Jupiter and Saturn. I mentioned they have millions of atmosphere worth of central pressure, and that actually lets hydrogen exist in this metallic hydrogen state as well in Jupiter and Saturn. Especially Jupiter has a big such layer because as I kind of mentioned, the Jupiter planet is really very different than anybody else. It's gigantic, very, very much larger, and has these other extra special features, okay? So now going back to Uranus and Neptune so that we can get to the moon of Neptune, which is the last giant moon to talk about for our own solar system, Triton, we will look at Uranus and Neptune, the planets. So just like Jupiter and Saturn are sort of in a league of their own, but really Jupiter a league of its own, Uranus and Neptune are sort of more the 2 planets that are sort of similar to each other, and they belong to their own sort of subcategory. So that's why we tackle this together. So Uranus and Neptune are twin planets, similar in their properties. Uranus is 3% larger in radius than Neptune, but 15% smaller in mass. Their internal structure, quite similar, like I mentioned. I just showed you those internal structures, with a layer of ordinary molecular hydrogen lying atop a layer of liquid water and ammonia, which is sometimes called ices in the jargon of planetary scientists. in turn lying atop a solid rocky core. Although the pressure at the base of the hydrogen layer is insufficient to compress hydrogen into its metallic form, for these two planets, Uranus and Neptune, we don't have quite as much pressure like as in Jupiter and Saturn. So although the pressure at the base of the hydrogen layer is insufficient to compress hydrogen in its metallic form, the layer of liquid water is electrically conducting. Thus, the rapid rotation of Uranus and Neptune produces significant magnetic fields. So it might not have metallic hydrogen. And remember how we also defined out a metal as something which basically has a lattice of nuclei, and the electrons are kind of freely flowing within the material. They're not so bound to each of the nuclei. So it's almost like this freely flowing type of electrons within a material that is now in its metallic form for whatever reasons, the pressure, the temperature, etc., is just right for it to become metallic, basically. Where a metal, let me read the official definition for you here so that it's completely clear. I think I already said it, but let me just say it again. So, a metallic substance is one in which a regular lattice-like structure of positive ions is surrounded by a cloud of delocalized electrons not bound to any particular atomic nucleus. So, basically, it's metal that's not solid. So basically think of it as almost like a solid, kind of, right? It's in its metallic form. But now I'm defining to you what we even mean by metals, because pretty much when we think about metals here on Earth, we think of something, as you said, something solid like iron. There are liquid metals though. In fact, does anyone want to say the name of a liquid metal? But basically, the more important feature of the metallic hydrogen is this metallicness of it, which to be a metal, all you have to do is be in this regular lattice-like structure of the, basically all the, all the nuclei are basically in a, all the atoms are basically in a lattice-like structure, and they're basically positive ions because the electrons are not necessarily bound to the nuclei of these atoms, but they're sort of more in a cloud of delocalized electrons. And these delocalized electrons are called conduction electrons, and they give metals their characteristic properties, which are, of course, being reflective, good conductors of heat, and good conductors of electricity. So both Jupiter and Saturn have high enough interior pressures to have layers of liquid metallic hydrogen. So it's a liquid, but it has that metallic property, like this was saying. So both Jupiter and Saturn have high enough interior pressures, actually it's like millions of atmospheres, to have layers of liquid metallic hydrogen. However, Jupiter, with its higher central pressure, has a much greater amount. So that metallic hydrogen layer for Jupiter is a lot bigger, like we saw in that ice cream cone picture. But that's the definition of a metal. To be a metal, you don't actually have to be a solid or liquid per se. It's more about the properties of a metal being met, which is basically having those conduction electrons, which make metals good conductors of heat and electricity, okay? So even though this environment within Uranus and Neptune isn't quite as high central pressure as Jupiter and Saturn, but there are still some interesting features. Okay, perfect. So although the pressure at the base of the hydrogen layer is insufficient to compress hydrogen into its metallic form, the layer of liquid water is electrically conducting. Thus, so the liquid water is basically more metallic in these planets. Metallic, like basically electrically conducting. Thus, the rapid rotation of Uranus and Neptune produces significant magnetic fields. So, what we saw, of course, with the Jovian planets is that they all have strong magnetic fields, and this is basically like why, right? We're kind of getting a deeper look at why that is. They have things that are, their composition is that they're composed of materials, and these materials might be existing in sort of a more metallic type of form. And when you spin such a thing rapidly, you will get a very strong magnetic field for the object. So both of them, with the rapid rotation and this conducting material within them, have a strong magnetic field. Uranus and Neptune are difficult to observe from the Earth. Although Uranus can barely be detected by the unaided human eye under ideal conditions, it was not recognized as a planet until William Herschel. I had to read that. I'm like, is that Wilhelm? No, William Herschel resolved it with his telescope in 1781 March. The existence of the planet Neptune was first deduced from its gravitational influence on Uranus. Wow. By the way, this book is right here. There you can see the name of the book, Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. We often use this book. I feel like we've been using this book a lot lately. And planets were not really my super duper expertise, so I am glad that the authors have been telling us so much about planets. But yeah, Uranus and Neptune are very far away. Let me tell you again the distances. That will give you an idea too, because you know we can see Jupiter with the naked eye sometimes, and so this will become clear when I tell you the distances of these things. These things are not all at similar distances or even that close to us or from the sun. So Jupiter is at 5.2 astronomical units from the sun. Astronomical unit is, of course, the distance of the Earth and the sun. And often that is used as a unit to measure other things, such as this. So Jupiter is still kind of closer-ish, but it's still 5 times away from the sun than us. Saturn is at 9.6 astronomical units, so almost 10 astronomical units. So another 5 times away from the sun, even farther away. And then Uranus and Neptune are very, very far away. Uranus is at 19.2 astronomical units away, and Neptune is at 30 astronomical units away. So they're very far. So it's going to be hard for us to see them. Plus there's, other geometry reasons as well. So Uranus and Neptune are difficult to observe from the Earth, although Uranus can barely be detected by the unaided human eye under ideal conditions. It was not recognized as a planet until William Herschel resolved it with his telescope in 1781 March. The existence of the planet Neptune was first deduced from its gravitational influence on Uranus in the 1840s, so a little bit later. So 1700s they were looking at it, but in the 1840s, two astronomers, John Couch Adams and Urbain Le Verrier, computed where the unseen planet had to be located in order to produce the observed perturbations to the orbit of Uranus. So that's pretty clever. They're basically looking at the sort of effects on the orbit of Uranus that Neptune is having, because they're not very close together, but there is still an effect that they have on each other. The planet Neptune was discovered by Johann Gottfried Galle in 1846 September, only 1 degree away from the position where Le Verrier told him to look. Wow. Thank you for beaming my teacher. Oh, okay, hello. Oh yeah, absolutely. We actually looked at how even the moons of Jupiter affect each other. They have orbital resonance, and the way the way the tides of Jupiter affect Io is different based on where it is on its orbit, again because it has orbital resonance with Europa. So all kinds of things. So similar thing here, not exactly the similar because these are two planets, but yeah, Basically, they looked at the perturbation caused on Uranus by Neptune. Since the maximum angular diameter of Uranus as seen from Earth is 4.1 minutes and that of, 4.1 seconds, and that of Neptune is 2.4 seconds, ground-based, so like the angular diameter can be given in like hours, minutes, and seconds, ground-based telescopes cannot obtain high resolution images of these two planets. Much of what we know about Uranus and Neptune comes from the Voyager 2 spacecraft. Thank goodness Voyager did its thing, which made a flyby of Uranus in 1986 January. Wow. Then a flyby of Neptune in 1989 August. Oh. In the Voyager 2 images of Uranus, the planet looked very uniform, without the colored bands that characterize Jupiter and Saturn. The image of Uranus, we will look at it. I'll show you the image of Uranus here. Banded cloud patterns on Uranus near the time of an equinox. Wow. However, an image taken, so they didn't think that there were a lot of bands on it, but then an image taken by the Hubble Space Telescope in 2006 August, more than 20 years after the Voyager 2 flyby, shows a distinct banded pattern in the atmosphere of Uranus. Hi, Ben! Hello! We're talking about Uranus and Neptune, and then we'll talk about Triton. I can't stay very long either, so I'm glad you're here. And you can always go back and rewind later on. So the change in the appearance of Uranus is linked to the planet's seasons. Wow. The axial tilt of Uranus is 98 degrees. Oh my gosh. That's a lot, meaning that its rotation axis lies nearly in its orbital plane. This causes extreme seasonal variations in solar heating. How crazy is that? Our rotational axis is tilted by 23.5 degrees, and we get seasons like we do. But look at Uranus. The axial tilt of Uranus is 98 degrees, meaning that its rotational axis lies nearly in its orbital plane. Hi, baby. Like basically, 90 degrees would be perpendicular to its orbital plane, right? But if it's tilted, holy moly, that's crazy. Oh, that is crazy. The most recent, so this causes extreme seasonal variations in solar heating. The most recent solstice on Uranus occurred in 1985 October, just 3 months before the Voyager 2 flyby. At this time, the northern hemisphere of Uranus experienced continuous sunlight, and the southern experienced continuous darkness. The resulting heat flow in the north to south direction disrupted the easterly and westerly flows that produce bands. Since the orbital period of Uranus is around 84 years, I mean, it is really far away. The succeeding equinox occurred 21 years later in 2007 December, just a year after the image that we'll show you was taken. Around the time of the equinox, the rotation axis of Uranus is nearly perpendicular to the Uranus-Sun line. Near equinox, a highly tilted planet like Uranus temporarily resembles a low-tilt planet like Jupiter, which has a theta of 3 degrees. Jupiter has hardly any tilt and has a Jupiter-like banded structure in its cloud layer. So near the equinox, it kind of resembles a low tilt planet. Uranus and Neptune, as mentioned earlier, are similar in mass and radius. They're also similar in surface temperature. They both have a temperature estimated from their infrared radiation of around 59 kelvins. So it's quite cold. Very, very cold indeed. This is odd, given that Neptune's distance from the sun is 1.56 times the distance of Uranus from the sun. Neptune is farther away. This implies that Neptune intercepts only around 40% as much solar power per square meter as Uranus. Because it's farther away. It doesn't get as much. When the energy accounting is done in full, Uranus is found to radiate about as much energy as it absorbs in the form of sunlight. So it radiates about as much energy as it absorbs. Wow. However, Neptune radiates roughly 2.5 times as much energy as it absorbs. This means that Neptune has an internal heat source, whereas Uranus does not. The reason why two very similar planets should differ so radically in their internal heating is not clear. And remember what we talked about the internal heating from Jupiter, which we thought came from basically its compression over the years. And for a planet as big as Jupiter, even a little bit of compression would basically mean a ton of change in its gravitational potential energy, and it comes out as heat. So we actually saw that Jupiter has a crazy amount of heat coming out, but it looks like we don't know exactly why there's a difference in the internal heating between Uranus and Neptune, because it seems like both of them have about the same surface temperature, which is odd because Neptune's distance from the sun is 1.56 times the distance. So Neptune is like quite a bit farther away than Uranus. So what that means is that Uranus is radiating about as much energy as it absorbs, whereas Neptune is radiating roughly 2.5 times as much energy as it absorbs, meaning that it has some kind of internal heat source. So something very interesting could be happening within Neptune that we don't yet quite know, which is so very interesting. If you want to study and research Neptune, there you go. There is something we don't know about Neptune that seems to be quite important. Yeah. So now we will talk about Triton, which is Neptune's moon, and it is the last giant moon that we will cover today, and we can always recap it, recap all of them again later. Neptune's satellite, Triton. Oh my God. There is such a cute picture of Neptune from the Voyager 2. And Triton. There is baby Triton. Baby compared to Neptune, of course. Neptune's satellite Triton is unusual in that it is the only giant satellite that has a retrograde orbit. This suggests that Triton is a captured object rather than one that formed close to Neptune. The retrograde motion of Triton has important implications for the evolution of its orbit. The Earth's tidal bulges act to increase the moon's orbital angular momentum. Thus, the size of the moon's orbit increases with time. So for our own moon, our tidal bulges act to increase the moon's orbital angular momentum. Thus, the size of the moon's orbit increases with time. However, for a satellite on a retrograde orbit, the pull of the parent planet's tidal bulges acts to decrease the satellite's angular momentum. The size of a retrograde satellite's orbit decreases with time. Oh, poor Triton. Triton's satellite orbit being retrograde, the size of it will decrease with time. The current size of Triton's orbit in units of Neptune's radius is around 5.9 radius of Neptune. However, as a result of the shrinking of its orbit, Triton will move inside the Roche limit a few billion years from now. Depending on its strength, Triton will either plunge intact into Neptune's atmosphere or be broken by the tidal forces into numerous fragments, forming a massive set of planetary rings. Guess who has a lot of rings? And more coming. All of them have rings. Saturn's are more famous, but they all have rings. And maybe they will even make more rings. They all have rings, actually. So planetary rings is actually the next section of this. All of the Jovian planets have planetary rings in their equatorial planes. The ring system of Saturn is the most massive, but the other three Jovian planets also have rings. So Saturn's rings are very massive and very famous, so everybody knows about the Saturn rings, but actually all of the Jovian planets, which is Jupiter, Saturn, Uranus, and Neptune, they all actually have rings. Many rings, yet not one divorce. Not only do they have many rings, there will be more, yet not one divorce. Indeed. Wow. Wow, wow, wow. I cannot believe what we have come upon. I cannot believe this. So many rings and more rings incoming. I don't think I knew that Triton will become a ring of Neptune, that Triton will in fact be sort of eaten by its parent planet because it's in a retrograde orbit and its orbit size is shrinking with time. It will take some time, maybe few billion years. But indeed, Triton will contribute to the ring system of Neptune, most likely. And how many cats do you have? Well, that's like asking Jupiter how many moons it has. You know, there are more being discovered all the time. Thank you, everybody. I must charge my phone now because it's dying. But indeed, I am a little scared now for Triton. Little scared. Indeed I am. For Triton. I have 17% charge, so I will keep chatting with you here, but I do need to show you the ceiling now because it's charging and it is on the whey protein container. And please do keep on chatting and telling us your comments. What do you think of Triton? What do you think will happen to Triton in a few billion years? Will it get, completely intact, like eaten by Neptune? Or do you think it will contribute to the many rings of these planets? Well, in this case, just Neptune. What do you think? Will it become a ring? Shattered? Who's shattered as in its heart will be shattered as it becomes a ring instead of getting married or staying married to Neptune? It will become a ring instead. Instead of staying married to its parent planet, or I guess staying adopted with its parent planet, it becomes a ring. Wow, what a travesty. Goodness gracious me. I'm just shocked. Today, all day, I've been shocked. I did not know that the Triton orbit was retrograde and it is going to be eaten by Saturn, or not Saturn, sorry, Neptune. I just did not know this, guys. Oh, that's my face. I am so very shocked. I am shocked. Oh, what am I doing? I was supposed to show you something. Let me show you the little itty bitty baby Triton next to Neptune, its beloved moon. Not moon, planet. Right here. That's itty bitty Triton. This is Neptune. Itty bitty. Itty the bitty. Let me read you the caption. This is the picture taken by the Voyager 2 spacecraft. 1 second. Let me make this straightened. This is the picture taken by the Voyager 2 spacecraft, and it looks back at a crescent Neptune above. So this is Neptune, this big thing, and a Triton below, right here. Little itty bitty Triton under Neptune. In your case, it's upside down, the book, but you get it. You get it. You see what I'm saying. I can't believe that Triton will become a ring. Oh my gosh, I feel terrible now for Triton. That is unbelievable. Shocking. Shocking news, guys. Breaking news. Shocking news. Hi, Baji. All right, I'm going to give them their din-din before I do my din-din. Shocking news. Just shocking. Complete shock. Well, at least, you know, Titan will not do that. It's just Triton. See, Titan, that's Titan. Titan, Saturn. Titan right there, Saturn right here. Saturn's disk, because of course Saturn is so much bigger than Titan, right? Titan, also a giant satellite of Saturn, is observed to have a thick atmosphere. So because it has a thick atmosphere, you can see this type of lighting. The atmosphere consists of mainly nitrogen, small amounts of argon, hydrocarbons, such as methane and ethane. And so that's why you get this backlit type of view. Refraction happening of the sunlight striking the atmosphere triggers the polymerization of hydrocarbons. Resulting long hydrocarbon chain consists of a smog layer, temperature and pressure close to the triple point of methane. Methane can exist on Titan in its gaseous, liquid, and solid forms. And so Titan has those amazing liquid lakes of methane and ethane. So I felt this was a much better story. Titan has those lakes, and Titan, this picture was taken by the Cassini spacecraft. So Titan is good. Satellite of Saturn. But now turn the page and please look at Triton, which will maybe not be there in a few billion years. That is so sad. Indeed. Extreme sadness right here. Yes, Baja. Let me give you your food. Oh, sorry, Suji. Come, Suji. Fuji. Come. Come, Baji. They're getting their din din now. How is everybody doing? Still good? Shattered, one more ring. Thank you so much for joining the live today. It was a shorter live, but and I ideally should have gone live in the afternoon. Next time I will do my swimming a little bit earlier so that I can still go live in the sunlight region of the day and show you the kitty cats while they're sunbathing and everything like that, and then we can do science topics as per usual. So I think Friday will shift a little bit earlier, and then of course Saturday and Sunday tomorrow we will go live earlier and stay live for a while. So certainly we will see you again tomorrow and Sunday, of course. Of course. So no worries about that. Oh my gosh, things are falling. Ugh. Whoops. Sorry, Baji. Here you go. Few billion years, right? I think Triton will see our downfall first. So Triton is Triton, okay? Triton. Poor Triton, though. Poor Triton. Triton. Yes. Triton won't go down without fighting. I love that, Ben. Triton won't go down without fighting. Triton, indeed. Triton will put up a fighting. For sure. Thank you, everybody. Thank you for so much for all your chat messages. Thank you so much for your comments. We will do a much longer live tomorrow. On Saturday, we will get it started as soon as possible, and we will keep going for probably much longer, late afternoon, evening time. And same thing on Sunday is the plan, because, well, it's gonna be pretty snowy and bad weather, I think, in Boston this weekend. So we are hoping that the live will be lively during such weather. So yeah, see you later. Bye. Good night, everybody. Good night. Triton with fighting. Okay. Okay. Hello, Fuji. Hi. Good morning. Yay. Good morning for you. Very nice. Good morning. Indeed. Good morning, pineapple. That's what I say to the kitty cats. Rich door. Rich door. Rich door. And pickly. Closed. 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 Okay. And off and off. And off. On. And off. And off. Very nice. Fuji, did you finish your dinner? Good job, Fuji. Come, come, come. Actually, I'll leave this out. You can maybe have a snack when I get back. Ooh, can we get 20 likes? That would be amazing. If we could get 20 likes. Please. good. Yes. Good morning, my